The first clue appeared in the orbit itself. Two dead stars locked in a binary pulsar system were circling each other in a way that suggested they were steadily losing energy. Their orbit was shrinking over time, even though no visible mechanism seemed capable of removing that much energy from the system. The anomaly was not subtle. Precise pulsar timing measurements showed that the stars were spiraling inward at a measurable rate, and the decay matched predictions closely enough to imply that something invisible was carrying energy away. Current models indicate that the missing energy may be leaving the system through gravitational radiation, but the process cannot be observed directly. A binary pulsar is normally expected to behave like an extremely stable gravitational clock. Pulsars emit highly regular radio pulses, allowing astronomers to track orbital motion with extraordinary precision. In most stellar systems, orbital decay occurs slowly through tidal effects, magnetic interaction, or surrounding matter. But these dead stars existed in an environment where many of those mechanisms were effectively absent. The system appeared too clean for ordinary explanations. There was no significant gas cloud, no strong external drag, and no visible material transfer large enough to explain the measured energy loss. Yet the orbit continued to tighten as if an unseen drain were extracting momentum from the system itself. The timing measurements became the critical observable pattern. Every pulse arrival could be compared against theoretical orbital models, and over years of observation, the discrepancy accumulated into something statistically unavoidable. The orbit was not remaining stable. It was collapsing inward at a rate that suggested a hidden physical process operating continuously. At first glance, the explanation seemed straightforward. Einstein's general relativity predicts that accelerating massive objects should generate gravitational waves, carrying energy outward through distortions in spacetime itself. A binary pulsar system, especially one involving dense stellar remnants, creates exactly the kind of extreme acceleration capable of producing such radiation. But the evidence remained indirect. No telescope could observe the gravitational waves leaving the system during the earliest measurements. Scientists were inferring their existence from orbital behavior alone, meaning the conclusion depended entirely on whether the decay model and timing interpretation were fully correct. That created the first major evidence gap. The observed orbit decay matched the mathematical prediction of gravitational wave energy loss with remarkable accuracy, yet the mechanism itself remained physically invisible. The system appeared to confirm the theory while simultaneously hiding the actual process responsible for the missing energy. The precision of the match created a deeper tension instead of resolving it. If the agreement was real, then spacetime itself was behaving like an energy-transmitting medium under extreme gravity. But if even a small unknown factor existed inside the timing measurements, the interpretation of the decay could shift dramatically. Some researchers considered whether measurement effects inside the pulsar timing process might distort the apparent orbital change. Pulsars rotate rapidly and emit narrow beams of radiation, and tiny calibration errors, propagation distortions, or environmental effects can accumulate across decades of observation. Current models suggest these factors are too small to explain the full anomaly, but the possibility never disappears completely. The contradiction became difficult to ignore. The cleaner the measurements became, the more confidently the system appeared to validate gravitational radiation. Yet the entire conclusion still depended on interpreting indirect evidence rather than observing the energy transfer itself. The binary pulsar effectively turned gravity into a measurable energy system. Orbital motion was being converted into something else, reducing the separation between the stars over time. But unlike electromagnetic radiation, the escaping energy could not be isolated or mapped directly through conventional observation. That limitation exposed a boundary in astrophysical measurement itself. Scientists could track the consequences of the missing energy with extraordinary precision, but the physical carrier of that energy remained partially inaccessible. The system revealed effects more clearly than mechanisms. As observations continued, another contrast emerged. Classical orbital systems are expected to conserve stable motion unless acted upon by an external force or dissipative process. In the binary pulsar, the stars behaved as though space-time itself had become part of the interaction, transforming orbital geometry into energy loss without any visible medium between the objects. The strange behavior became even more significant because neutron stars are among the densest known stellar remnants. Their gravitational fields compress matter into extreme states where ordinary intuition begins to fail. Small uncertainties inside such environments may produce consequences large enough to reshape how orbital decay is interpreted. That uncertainty introduced another unresolved layer. The pulsar timing data measured motion with extraordinary precision, but the internal structure of neutron stars remains only partially understood. Current models disagree on aspects of their density distribution, magnetic field evolution, and internal matter states, all of which may subtly influence orbital behavior. The system therefore occupied an unusual observational position. It was both one of the strongest confirmations of relativistic gravity and one of the clearest demonstrations of how dependent modern physics is on indirect inference. The orbit decay appeared measurable, but the deeper mechanism remained physically abstract. As the stars spiraled closer together, the energy exchange accelerated. Faster orbital motion increases gravitational interaction strength, potentially amplifying the invisible transfer process over time. The closer the stars moved, the more violently the system appeared to distort the surrounding structure of space-time. Yet even this interpretation carried limits. The orbital decay could be modeled mathematically, but the actual structure of space-time distortion remained beyond direct visualization. Scientists could describe the geometry through equations and measurements, but not observe the energy flow in a conventional physical sense. The anomaly therefore persisted in a partially unresolved state. The system strongly suggested that gravity under extreme conditions behaves dynamically rather than statically, allowing orbital energy to escape through space-time distortion itself. But because the evidence emerged primarily through timing analysis, the conclusion remained tied to the reliability of the measurement framework. Another contrast slowly became unavoidable. The binary pulsar appeared predictable enough to function like a cosmic laboratory, yet the deeper interpretation of its behavior depended on phenomena that could not be isolated directly. The stars were behaving exactly as expected and still revealing something fundamentally inaccessible at the same time. Over decades, improved instruments reduced many sources of observational uncertainty. Pulse timing became more precise, statistical confidence increased, and additional binary pulsar systems showed similar decay behavior. Instead of eliminating the mystery, however, the growing consistency reinforced the idea that invisible gravitational energy transfer may be a real physical process operating throughout the universe. But the evidence gap never fully closed. The systems revealed what gravity appears to do under extreme acceleration, while leaving open deeper questions about how space-time itself carries energy, whether gravitational radiation is fully understood at all scales, and whether unseen measurement assumptions still shape the interpretation of the decay. The binary pulsar ultimately exposed more than a shrinking orbit. It revealed a region where observation begins to outrun direct physical intuition. Two dead stars appeared to lose energy into something that cannot be seen, cannot be captured directly, and may only be understood through the changing motion left behind. The implications became more severe once scientists realized that orbital decay in binary pulsars was not occurring as a single isolated event. Multiple systems observed across different regions of space appeared to follow similar long-term patterns, suggesting that the hidden energy transfer process may operate universally under extreme gravity rather than inside one unusual stellar pair. That consistency created a new constraint. If the measurements were broadly correct, then gravitational systems throughout the universe may slowly leak orbital energy through mechanisms that remain only partially observable. The anomaly was no longer confined to one binary orbit. It potentially extended to gravity itself. The deeper problem emerged from propagation. As the stars lose orbital energy, their separation decreases, increasing orbital velocity and gravitational acceleration simultaneously. Current models indicate this creates a feedback process where stronger acceleration generates even greater energy loss, causing the decay to intensify over time. The system therefore does not remain stable as it evolves. The closer the neutron stars move together, the more extreme the invisible transfer process appears to become. Small deviations in orbital distance may eventually amplify into dramatically different long-term outcomes. But the timing measurements themselves become harder to interpret as the orbit tightens. Faster orbital motion compresses pulse arrival intervals and increases relativistic distortion effects inside the signal structure. The cleaner the system appears mathematically, the more dependent the interpretation becomes on assumptions embedded inside the timing framework. That dependency introduced a subtle analytical tension. The observed decay may strongly support gravitational radiation, yet the conclusion also relies on models built from the same relativistic framework being tested. The evidence appears self-consistent, but the system partially validates itself through its own assumptions. The contradiction remained unresolved. As observations expanded across decades, another consequence emerged. Binary pulsars do not simply reveal missing energy. They reveal that orbital systems can evolve through interactions with spacetime geometry itself, even when no visible medium exists between the objects. This changes how stability must be interpreted at stellar scale. In ordinary mechanical systems, decay is usually associated with friction, collision, or matter transfer. Inside the binary pulsar, the system appears capable of degrading through geometry alone, suggesting that spacetime under extreme gravity behaves dynamically rather than passively. The anomaly became more difficult to isolate because the energy transfer cannot be localized precisely. Scientists can estimate how much orbital energy disappears over time, but current observations cannot map exactly where that energy exists during propagation. The system exposes a measurable consequence without revealing the full physical pathway. That observational limit grows more severe at larger scales. If gravitational radiation spreads outward across vast distances, its intensity weakens dramatically before reaching detectors. The original energy exchange may remain mathematically detectable while becoming physically inaccessible through direct observation. The pulsar timing data therefore carries a hidden asymmetry. The orbital decay can be measured with extraordinary precision near the source system, but the escaping energy rapidly dissolves into the larger structure of space-time. The farther the effect propagates, the less directly observable it becomes. This creates a widening evidence gap between local observation and large-scale verification. Another escalation appeared when researchers modeled long-term orbital evolution. As binary pulsars continue losing energy, the stars may eventually approach merger conditions where gravity becomes violently nonlinear. Under those conditions, current equations become increasingly difficult to solve cleanly because relativistic effects intensify faster than observational certainty. The system begins crossing into a boundary regime where prediction depends heavily on approximation methods. Small uncertainties inside neutron star structure, spin alignment, or mass distribution may propagate into major differences during the final stages of orbital collapse. The closer the system moves toward merger, the less stable the models become. The pulsars therefore expose an instability hidden inside precision itself. Early orbital behavior appears orderly and measurable, but long-term evolution gradually amplifies uncertainty as extreme gravity strengthens. A system that initially functions like a perfect clock slowly transitions into one of the most difficult gravitational environments in astrophysics. Even the concept of energy conservation becomes harder to visualize intuitively in this regime. energy is not disappearing randomly, yet it also cannot be tracked through ordinary physical transfer mechanisms. The orbit shrinks, momentum changes, and the surrounding space-time may carry away the difference through distortions that remain fundamentally invisible. That invisible propagation introduces another unresolved dependency. If gravitational energy cannot be localized cleanly inside space-time geometry, then the exact meaning of energy transfer under extreme gravity may itself become partially model-dependent. Current physics describes the effects successfully while still debating aspects of the underlying interpretation. The anomaly, therefore, evolves beyond orbital decay alone. What first appeared to be two stars spiraling inward now exposes a deeper uncertainty about how gravity stores, transports, and redistributes energy across space-time. The system also challenges observational timescale itself. Most human observations capture only a tiny fraction of the pulsar's total orbital evolution, meaning the long-term interpretation depends on extrapolating behavior far beyond direct measurement windows. Current models suggest the decay process remains stable across immense timescales, but the full evolution can never be observed in real time. That limitation forces astrophysics into a partially inferential position. Scientists observe fragments of a much larger process and reconstruct the unseen stages mathematically. The orbit decay appears continuous and predictable, yet critical portions of the causal chain remain permanently outside direct observation. As the stars continue tightening their orbit, the hidden process appears increasingly violent while remaining observationally indirect. The stronger the gravitational interaction becomes, the more the system suggests that space-time itself participates actively in energy exchange under extreme conditions. But the final boundary remains unclear. Current models may describe the decay accurately, yet they still cannot fully explain what gravity fundamentally becomes when acceleration, density, and space-time distortion all intensify beyond clean observational access. The binary pulsar no longer appears to be just a collapsing orbit between two dead stars. Current observations strongly suggest that the system is revealing a real transfer of energy through gravitational distortion, narrowing the range of possible explanations significantly. Yet the mechanism remains visible only through its consequences, not through direct observation of the process itself. That changes what the anomaly represents. Earlier models treated gravity primarily as a force-shaping motion, but the pulsar data suggests that under extreme acceleration, space-time may actively participate in transporting energy across the system. The orbit decay appears measurable with extraordinary precision, while the deeper physical pathway remains partially inaccessible. The boundary emerges at the point where measurement and interpretation separate. Scientists can track the shrinking orbit, calculate the missing energy, and model the decay with remarkable accuracy. But current physics still cannot fully localize how gravitational energy exists during propagation through space-time itself. The equations continue to describe the behavior more cleanly than the underlying reality can be observed. The closer the neutron stars move together, the sharper that boundary becomes. Extreme gravity appears to amplify effects that remain mathematically predictable while becoming physically harder to interpret intuitively. The system behaves consistently enough to strengthen the theory and strange enough to expose what the theory still cannot fully explain. What remains unresolved is no longer whether the stars are losing energy. The unresolved question is what gravity becomes when space-time itself appears to carry that loss through a process that can reshape an orbit, distort motion across light years, and still remain fundamentally invisible except through the changing path of two collapsing stars.